All right, so this section, we went through a lot of the different system components. Now, today, what we're going to do is we're going to look at heat transfer, heat generation. Some of it we're going to skip over, like getting in too much into the weeds on a lot of items, but most of these presentations, what I do is I have many slides on each item that we're touching on, and they're just hidden slides. So if you really want to get into some of these things, you can unhide those slides and you can see a lot more detail. So the process I figured to go with is start off with some basic heat exchanger items. Then from there, work into types of heat exchangers, uh, qualities of heat exchangers, just go through some software items. Now, today I'm going to use our software for heat exchangers and for pumps. A lot of other platforms, everybody's doing the same thing. So if you become familiar with one, you probably become familiar with most. It's just often finding where tools are. So I'll run through heat exchangers, some of the software selection items, do a little bit on the pumps while we're on the selector, the online platform. And then from there, talk about just what we're seeing out there for what items, as we see the gas transition, electrification, decarb approaches. And then from there, any questions, we can make any curves we need to. All right, so starting with basic heat exchanger types and heat transfer. All right, let's try this. That's not working. Oh, all right, so if I sit down, all right. All right, that's just a little bit of the outline. Some of these items are skipped, so if you do anything more in depth, like I said, the hidden slides. So what is a heat exchanger? Heat exchanger is a device that's used to be able to transfer energy from one item to another. So whether it's water to water, air to water, water to air, however it may be, refrigerant to water. It's a device just so whether it's a plate and frame, shell and tube, we'll go through a couple of these different items. But ultimately, the idea is that they're exchanging energy. So the hot coming in is going to cool down. It's going to become cooler. The cooler one will then get warmer. It seems makes a lot of sense. So these are the ones that you're most likely going to be seeing in any sort of commercial building application or just in general across our industry. So on the far left-hand side, sorry, here's my phone here. On the far left-hand side, you've got we call our BPHE. It's a braze plate heat exchanger. So it's that's one that the plates are braced together. You don't have a gasket. The unit on the far right, that's a frame. Also plate. It also has plates, but this one's in a frame, so has gaskets in between. You can remove, service the heat exchanger. The one in the middle, that's a shell and tube. The type is U-tube because those tubes that are on the inside actually bend and come back. But there's also many variations of a shell and tube. So when tubes are straight, you can be creative with the different options. On the top right hand side, that's actually a image of what it would be with a straight tube heat exchanger. So if in this case you would have you would have it as a single pass versus U-tube. Those internal copper lines would then bend and come right back to the head. This I don't have a slide directly on it, but I think it's good to understand a lot of the different components. So you've got your head down below. So on the bottom right, you've got your bundle, your tube bundle. And so that's got your cover plate with your different copper tubes that you either have that U-tube or your straight tube. You have your head. The head is where you may see your hot come in, your cold come out. There's a divider, so maybe the hot comes in the top, it goes around that bend and then it comes back out, and that's where the hot outlet would be, the cooler of the two hots. And then you see that there are ports on the shell, and that'd be your shell side. And so same idea. You'd have your inlet outlet, just so you have a little bit of a picture for it. So for the shell and tube heat exchangers, the big advantage to these that you'll see a lot of people selecting is that you have a lot of options for materials. So if you want 316, 304, whatever material type you want, temperatures, pressures, it's a very wide range. They're pretty easy to make to custom manufacture, unlike maybe a plate and frame where you're not going to be making so many custom patterns. Even though you'll get custom mixes, you'll have blends of different plate patterns, but most likely it's you see a lot of that. Low heat transfer rate is one of the disadvantages. You think of that as just in terms of the amount of surface area when you compare it to other designs. And the limitation, we're going to get into temperature approach and temperature cross. So this says here a 10-degree minimum is what they would like to see, but I'll actually come back to that after the slide. So with the brazed plate units, really just the plate types in general. There's a high heat transfer rate, so you have a nice turbulence to it. There's a recommended of a minimum of a 2-degree approach. So remember that's quite a bit lower. It's great for temperature cross. A disadvantage is obviously limited configuration. So like a brazed plate unit, you may be able to get it with like a copper nickel or a nickel braze if you need something to be more resilient for maybe a pool application, versus if you have a plate and frame, you have a few more options where you'd say, okay, instead of one or two options, you could say, okay, I want to do titanium and I want to have these type of gaskets and this type of connection. But as you can imagine, when something can be assembled, it would make sense that it would be easier to configure. So those are the two plate type heat exchangers. The bottom is the brazed plate, then the plate and frame up top. So for the plate type, just going on the advantages, higher heat transfer rate, closer temperature approaches, temperature cross, we mentioned that. So you'll notice a lot of these will have these different patterns, and these different patterns create this different flow characteristics among the plate. So as the water's traveling through, depending on that flow pattern and where that turbulence occurs, that's really going to influence its ability to transfer that heat. And something that we go through it a couple times throughout this presentation is just getting the idea of that turbulence and that exposure, that turbulence accelerates that heat transfer rate. You think of it as like if you put an ice cube in a bottle of water, and you just if you took track of how quickly or how slowly the temperature were to change versus if you were to shake that bottle, it would clearly accelerate it through that turbulence and that exposure. So you think of the same thing when it comes to these heat exchangers. We'll get a bit more into some of the equations, but start thinking of as you start seeing these higher pressure drops, if it's not due to the connection, it's due to that turbulence. And so you often see, as allowable pressure drops go up, you'll see the size of the unit go down. And what that boils down to is really you need to find the sweet spot for your application. And another thing we'll mention a few times, there's always a trade-off for something. So let's say if we say, okay, we're going to decrease our upfront cost, and we're going to, by having a smaller heat exchanger, by allowing higher pressure drop, well, our operating costs are now likely going to increase, right? So, I guess as system designers, what we have to try to do is have at least a grasp of all of the variables that we're having to balance for the best solution. So just keep that in mind. So say there's a couple different thickness. We'll talk about that with the selection. For any heat exchanger, and really just this comes up very often in whether it's providing calculations, whether it's for a domestic water system, whether it's for space heating or cooling. It's just really that heat balance equation or the heat heat transfer equations. We've got a couple of them here. This is one of the more basic. So you might hear somebody say, all right, 500 so if someone says it's 100,000 BTUs and they're looking at a 20-degree delta. You have a lot of people that might say, 500 multiplied by the delta multiplied by the GPM gives you those BTUs an hour. So you say 10 gallons a minute, 20-degree delta, 100,000 BTUs. And that's a bit of a rounding, and it is pretty good estimate in ballpark. But I'm sure that as you progress in your career, you'll probably be able to spit most of these off. But ultimately, this is where this comes from. And this is mentioned here because in a liquid to liquid situation and no phase change, is that we need to make sure that we're properly calculating the load and that sides balance. It's very often we look at a schedule and things don't make sense. Like you'll see the load, you'll say 2 million BTUs, but you'll see a flow rate and a delta that doesn't align with that. Now these are the items that are factored. So just to keep this in mind. So whether you're even saying how many BTUs are in this tank that are above 40 degrees, if you were doing a domestic water system and trying to figure out usable volume, and you'd be able to say, okay, well, I know that a British thermal unit or BTU is 1 pound by 1 degree. It starts making sense why we take 1 gallon, multiply 1 gallon. We're looking at GPM, we're looking at 1 gallon. 1 gallon weighs 8.34 pounds per gallon. So that's the weight, just for some of the calculations, but making sure that they're equal. And that's the item that's mentioned down below.
Say liquid to liquid. I have one that I'm using at home that is
For refrigerant?
your own refrigerant.
Yeah.
And that means there are gases inside.
Yeah.
Is there anything changed? How do we do it?
I mean, what I would, and so you've got water on one side would be able to do it. The other side, I would imagine that you'd have to factor in a specific gravity at it at that state. Because its density would be different. So you'd have to factor in specific gravity, I imagine, when you're factoring. So this isn't for the refrigerant, but on the other side, you have water. Is that right?
Got water on one side of the refrigerator.
Yeah. So so you could always calculate it with water doing this, but in terms of the refrigerant, I would imagine that other than calculating from the water, you'd probably have to know the exact phase of it, the phase, the temperature, so you determine density and so on. So something that sounds a bit more complicated than it really is the log mean temperature difference. Ultimately, the further away let's say if you have two fluids, and the further away that those two fluids are from one another, the more quickly, the easier it is to transfer heat, right? So it always wants to go from hot to cold and wants to transfer. As you start getting closer in temperature, it's harder to make that transfer, holding everything else constant, surface area, exposure. So this right here just goes a little bit about how the importance of having a reasonable log mean temperature difference, which you'll get into actually a bit more in another slide. But the value of, you'll notice that on these heat exchangers that we've got a counter current. So the hot's going in one side is the same side or the same portion that you see the cold coming out of. So having that counter current is what actually gives you the greatest temperature difference exposure over that period. So the approach temperature for the counterflow is a hot in minus the cold out. So you've got your hot in, and we've got an example on the next slide. So we didn't make up numbers. Temperature cross is when you have, let's say if your cold out is greater than your hot out. This might be the best example. So if we look at the HI up at the top right of that chart here, that's hot in, hot out is that same curve at the bottom. That's hot out. And you'll notice is that, so cold comes in on the bottom left, hot goes in on the top right, and they're going in the opposite direction, counter current. Where the cold out is exceeding the hot out, that's our temperature cross. You're sure you're familiar with what the temperature cross is. And then the approach is the difference between let's say that hot in and the cold out, how closely that cold out is able to achieve that hot in. And then on the opposite side, the hot out and the cold in. And so these two approaches are essentially used to calculate the log mean temperature difference. So if these two temperatures are exiting at very different temperatures than the opposite started at, then you can have a very, very large LMTD. So this is just giving an example of that, where it actually puts some temperatures to it. Where, for instance, if you have 95 degrees going in, 85 leaving, on the hot side, the cold side going in at 73 and leaving at 82, then we notice that at the top, the 95 minus 82, that gives us our 13-degree approach. On the bottom there, 85 minus 73 gives us a 12-degree approach, and then we would plug that in very close to just averaging. And so ultimately, I think like a log mean difference is that it's trying to provide a number for something that's not a straight line, it's a curve. So the further these two fluids are, these two medias are apart in temperature, the further they are apart in temperature, the quicker in which they transfer heat, but as they start approaching one another, their rate of transfer starts reducing because they're closer in temperature. So it's just trying to pinpoint a spot. Yeah, so this would be more so of like, I guess we'll use it in a second actually for its impact on like surface area. Now this is just this could be so if we add flow rates, then we'd be able to. That's when if we had load, we'd be able to use these to be able to determine flow rates, or if we had flow rates, we'd be able to then determine load because we have the inlet outlet temps. But there's also other things where like if you had surface area and you had some of the temperatures you could work into, but these are just ideal scenarios of without any load. But the whole point of it was that on the left-hand side, you'll notice that we have a counter current. On the right-hand side, we've got that co-current. So the hot and cold are going in, coldest and hottest are starting together, and they're leaving. And if you take the approach of the hot and the cold, or the exiting and entering for the co-current, and you take a look at that log mean temperature difference we calculate, you'll notice that reduction in the LMTD would require essentially 25% more surface area. So if you have a higher LMTD like the left-hand side, that would be 25% less heat transfer. You get 25% less heat transfer if you have the lower LMTD. I think we've got just it. I think this is the next slide. We keep editing these. So all this is really showing is that the relationship, so all right, so Q is load, U is heat transfer rate, A is surface area, and then LMTD. So with everything else held constant, and let's just say changing one variable at a time, as it would make sense, as you increase your turbulence, you increase your heat transfer rate, whether it's because you have that greater entering separation, increase your heat transfer rate, the required surface area would go down for the same heat transferred, which would make sense. And then as the higher your LMTD, the lower the required surface area to perform the same or achieve the same heat transfer. So like what we had on this backside, this was just showing that if you hold all heat transfer, well, I guess we also have to factor that's co-current versus counter current. So ultimately, counter current gets the best heat transfer. Co-current is about a 25% reduction. Sometimes you'll hear people say that the heat exchanger was piped incorrectly. Now, as long as it was done consistent, so as long as you have that counter current, whether you put the hot on what was supposed to be the cold side or the cold side on what was supposed to be the hot, it's fine as long as we've got that counter current. That comes up sometimes. So, and then, yeah, so we can reduce our surface area by having a greater LMTD, but a lot of times these are factors that are outside of our control, right? So we have conditions that we need to achieve to be able to satisfy other components in the system. So it's rare that we're able to really pick those. But if you are in a position where you can influence some selections that will influence the heat exchangers, and this is one item that you can consider when you're determining those temperatures. So I'm kind of burning through this slide because I wanted to get this done the earliest because I feel like these slides are probably not the most interesting. And I think once we start getting the selections, it'll be better. Ultimately, with heat transfer, we'll get into this in the selections in a little bit, but you need to have at least a handful of these to be able to determine. So if you have your hot inlet outlet and you've got a flow rate, then we know our load. But we don't know, but we wouldn't tell, but then to be able to know the cold side for the whole heat exchanger, we'd have to have like an entering water temperature or leaving water temperature. So a combination of about 5 of these. I noticed that this slide is wrong. It says 5 out of 7 of these are needed, but it's not just, but there is a combination you could technically do where, like for instance, if you did hot in, hot out, and flow rate, we would already know our load. So load shouldn't be then counted out of that 7, but we'll do that in the software. Allowable pressure drop. So you need to have these items to be able to determine what conditions, and then you need to have, say, your pressure drop. I think the default on our platform is 10 PSI, but I often change it to about 15 feet ahead. Mechanical requirements, so any design constraints, materials, space. So whether it's our the height of the heat exchanger or the frame sometimes can be very large. So you'll notice in the platforms, we'll give the dimensions so that, that can be a factor, and then you can see the relative price as well. All right, so here's an example where, for instance, we've got ultimately what it's showing is that based on what we have here scheduled at the top, down below, it's just showing is that when you use that, when you determine that load based upon the flow rate and delta, that both sides are even. So often on these schedules that things won't make sense. You'll see things in imbalance. So the problem with that is that a lot of times people might even just select it off what they think you're looking for. And especially as we start scaling some of these projects out, we want to make sure that that's not the case. So quite often that's what I'll do is when things don't match up, I'll be reaching out to someone. But it's important to make sure these balance because if these don't balance, there's a lot of other items that are based off of these, whether it's your pump selections, which then lead to the trim selections, and but it's pretty simple to do, obviously. Yes.
With
Yeah.
that slide, how does it work that the chilled water is heating the tower wall? Or abutting the tower wall?
So this was
Never abuts the tower wall.
I think this was just giving both sides of the heat exchanger. So for the heat exchanger selection, they're providing the entering and leaving water temperatures for both sides.
What do you use such change it for?
That's
Because you never let the chilled water touch the water top.
so yeah, you're in. Well, yeah, I mean, right here, we were talking about putting in a heat exchanger.
Just
Shouldn't be
for
touching.
exchanger purpose, okay.
Yeah, it wasn't, yeah, these wouldn't be touching. These would be just through a heat exchanger. And so that's another thing. With all these heat exchangers, no normal circumstance would the fluids on either side be in contact. Yeah, this is just another example of just trying to show the LMTD. So another thing is that if the approach is the same on both sides, it would make sense just looking at the equation is that it really is it would just be that approach. So if the approach on the right-hand side were 3, and then on the top left-hand side, if that were 3, if they were both 3 degrees apart, then your LMTD would be 3. But ultimately, let's see here. Let me skip out of these slides. So in this case, we've got the chilled water, the tower water. We have the entering water temperature 57, leaving at 53, 51, and 54. So in this case, we have temperature approaches of 3.6 and 2 degrees, or about just over 2, so the 2 degrees. What kind of heat exchanger would we use? Would it be if you have a very close temperature approach, would you use it'd be a plate heat exchanger? So I'm looking at, I got to reformat this this little section here because I think that what we need to do is probably describe the approach before listing it, because I think originally we started off talking about the qualities of each of the heat exchangers before describing what those qualities meant. So what they say is with a shell and tube heat exchanger, you don't generally want to make a selection that has an approach any less than 10 degrees. And then for like a plate style, a minimum of 2 degrees. And you'll notice, so as that approach gets smaller and smaller, and we're trying to squeeze every bit of the difference out, the size of these heat exchangers and the required surface area is pretty great. I think we can skip past some of these examples here. We don't need to really get into too much of the LMTD. All right, we can skip some of that here. You'll notice a lot of the selections just across the industry, just so people are familiar about it, is just about every device out there, whether it's from boilers to heat pumps and chillers. There's usually third-party testing. Now, for heat exchangers, specifically the plate and frame style heat exchangers, there's what they call as AHRI standard 400. And so what AHRI is, I'm sure you've heard of it, but it's the Air Conditioning, Heating, Refrigeration Institute. And that's a lot of trade members and companies. So companies like Bell and Gossett and Lochinvar and many of our brands and many other brands that others represent are all members of this organization. The benefit really of the organization is to kind of work together as a group to make sure that everybody's providing products that are comparable or at least measured comparably, right? So if you don't have that there's always a test procedure. So in this case, it's plain frame heat exchangers, and they provide a certification. It's HRI 400, and it's just highlighted a couple of these things on here, just so that what people are claiming is actually the case. Now, it doesn't apply to all applications, so it doesn't apply. So it doesn't apply to shell and tube. It doesn't apply to braze plate. It doesn't apply if the system is only glycol. There's a lot of things that technically do not require AHRI 400. But you'll notice that most all manufacturers that are that are uh, any member that's certified to these standards, they have to do what they call a certify all. So even if the spec doesn't call out for it, but the use is at least if any of the use for that heat exchanger is supporting the conditioning of space heating or cooling, that all participating manufacturers have to provide a standard 400 certified unit, which is nice, so that most heat exchangers out there are likely participating. Any of the bigger names, there may be some smaller companies that may not, but just so when you see it, that's the value of it. Now, there are less expensive ways to make selections with likely this almost the same exact units. In our platform, I'll show you that we can unselect, it comes default selection, I think, is HRI 400, but you can move it over to commercial or to industrial. And what those do is they essentially, I think they remove a bit of safety factor. I think a lot of these have a little bit of a safety factor so that when they are tested, which they have to be sampled every year, that you're not going to fail and lose your listing. And that's another thing too, is if a manufacturer knowingly supplies, like if we knowingly supply a non AHRI 400 standard verified product for something that we know is space conditioning, there is a Bell and Gossett can lose their listing. So that's why, if people are always submitting on it, they're forced to. But at the same time, at least it's tested. So it's just a little bit about the scope, and that's basically for HVAC items. A couple items that are exempt. I mean, if we're talking 20,000 gallons per minute or 240 million BTUs an hour, any of that stuff is excluded. But I think what it should more likely say is like glycol. If it's a glycol, technically it wouldn't, but we will if it's anything that has to do with space conditioning. Second, I got a note on here. Screen sharing stopped. Hey, Joe, can you see it now? Looks like that happened more than 10 minutes ago. Okay.
Yellow pause. There's a resume button in the menu bar.
Oh, shoot. Good call. I think this is about the end of this little piece here. I was hoping to cruise through this pretty quick and not spend too much on it, but I think we're already 40 minutes in. Here we go. Yes, that's AHRI 400. Just without boring everybody too much on that. Okay. There we go. And then let's go to here. And okay, so this is just a drawing that would be selected, but I'm going to jump into the sizing, just so that some of this I hope some of it will all kind of come together. Actually, I'm going to go back here. So when you when you go to ESP-system-wise or Bell and Gossett system-wise, if you go to that, it brings you to a sizing platform. I had the link set up so it goes directly to the heat exchanger page. So there's different tabs, pumps, so on. So let's say if I select Open ESP Thermal, if you create an ESP system-wise account, it'll transfer your credentials over to the thermal. So let's say if we were to just walk through it and say, begin a new selection. And if we were to go along, we'd say, okay, let's say a gasketed unit. This is where I mentioned about the AHRI standard 400. That's the default setting. Most often, that's going to be the case. A few times it might break away, like if we're doing a pool heating selection or something that's, far from space conditioning, then we break off and away from them here. So this is where you'd select if it's water to water, it's a single phase item. If it's a steam condenser, so if we're looking to use steam in the unit, so like a steam to water application, or then do steam condenser. It's all pretty intuitive. So let's go in and just taking a look at that heat balance equation. So if we were to have 60 gallons a minute, 120 in, 100 out, 60 gallons a minute, 70 degrees in, we have enough here to where this will tell us the load, right? So we've got inlet outlet flow rate that gives us a load. And then if we have inlet and we have flow rate with the load, it'll come back and it'll solve for our outlet. So that a lot of times people will say is that you're just letting a variable float. Just saying is that it's not it's based upon the other information, we'll let it be calculated. And so in that case, you see, 89. Now, if for instance, keep in mind that if you were to change it and you were to do, let's say, 30% glycol, and obviously then our verify input, and I think it's not that drastic. But a lot of times if you see something in you see like a in the tenths or hundredths for something on a schedule, a lot of times that'll be because that's the variable that they had floating. Here is where the next, just walking through it, your pressure drop default is 10 psi, but keep in mind that upfront capital cost. If you do select something at 10 psi or 23 feet ahead, at least the potential for that when you go through the selection, there's obviously your pump's going to be consuming more power, and so. What you can do sometimes is you can start it at 10. I like to start it at about 15. I think that's a reasonable balance. So we're going to do 15 feet ahead. Select that for both. And let's increase this flow rate to 300, 200, and then let it float. So we get a little bit larger. Down here, NSF, so if we were to have that for, let's say, a potable water system, then we'd want to select that. And all that really does is it just kind of gives you a safety net where to make sure that you do select components that are rated for potable water. You don't have to select that to go through and select it. It just kind of walks you through a little bit easier. All right, so moving on, if you had a heat exchanger possibly that you had in the field and you said, I wonder what I can do to that heat exchanger. What you could, well, in terms of performance, you can put performance in, then you can select rating. And then what I could do is I could then say, okay, I have the heat exchanger details, which we could pull the serial number. We could build it and we say, okay, you can achieve those new conditions with that old heat exchanger, or maybe you add X amount of plates and we can achieve it. Just so you can kind of go back, and it's just a nice tool to have. So let's say if we were to go through and instead make a selection. I'm going to go back to selection, verify my inputs. Here's our temperatures, mechanical details. The default's going to give us that just is going to give us our standard thickness here. You can edit this obviously if you're going to go to titanium 316 plate mixture. I let a lot of this float so that it really just comes up with the optimal selection rather than having it be forced into a certain pattern or that I would select. The only time I would really change materials is when depending on the application. So like if you do have something like a pool heating or something that's a bit more aggressive for a fluid, titanium's usually a great option. 316 is all right, but at the same time, it has its challenges in comparison. But obviously, there's a cost that's included with the titanium. That's a bit more of a premium. So single wall versus double wall. So if you wanted to have an air gap in between, let's say that there's a hole in the heat exchanger rather than high pressure leading to low pressure, whichever side that is, that if you have that air gap that it's able to run out and doesn't actually penetrate to the other side. So especially when as you start having, if you have anything that's toxic, obviously, if you have anything that's critical, but one thing to keep in mind with that really is that as we put that air gap in between, air is a great insulator. And so you think about that plate's ability to transfer heat and then its ability as it is versus having that air gap in between, it's going to require much more surface area and more turbulence to be able to achieve that same heat transfer if we've got an insulator in between every one, right? So just keep that's always has to be kept in mind. But
Wall.
so it's not, yeah. And I think when it comes to potable, it depends on what state you're in and what their adopted code is for like IPC. Last time I was looking is that it depended on the difference in pressure. So if you had a relief valve setting on a non-potable, but like a boiler circuit, and you're at like a 75-pound relief valve, but then you've got a 60-pound PSI coming in on your street. If there was any leak that you could cross-contaminate. So to my understanding is that if there was the pressure, if the non-potable system pressures were greater, or the relief valve was greater than the operating pressure of the other side. The other thing is they categorize like toxicity of different fluids, and I think, however it is, surprisingly, propylene glycol is in a very low category. I'd be more concerned about everything else in the system, all the magnetite and iron oxide and debris, and sometimes you even have bacteria growing inside of the pipe. So, but yeah, no, I think that when you select the NSF, it just makes sure is that your nozzle or like your connections to the unit are also like a stainless steel versus versus the standard.
This is only one that we click on it.
Yeah, let's see here. And but yeah, it reminds me of like single wall heat exchangers for like indirects. You'll see a lot of indirects out there, all single wall. Now, depending on the state, it's different codes. Like in Massachusetts, they've got their own plumbing code here, and so single wall, as long as you have a non-toxic product on the other side, there really isn't any restrictions on it. Now, other states that have adopted some of the, I think, newer plumbing codes that don't have their own, there are some limitations on pressures. I think that you can use a single wall heat exchanger. Years ago, God, it had to be 12 years ago. It was actually anyone here from Weston and Sampson?
Yes.
Okay. So it's probably about 12 years ago. I was in tech support and they asked me to I got a call, and I think it was Mariano back then. What he was doing is he was making these selections for the Packers stadium. And so we were making the selections and we put all of these together, and then come to find out that the local code was requiring double wall for the pools. And these were titanium heat exchangers. I mean, these were really, really, really expensive heat exchangers for this place. And lesson learned of like, here in Massachusetts, we might think that, we have everything covered, and anything that's code here is probably more strict than everywhere else. Well, sometimes other states have these really progressive or greater safety codes. So yeah, I think all those heat exchangers were ordered and had to be reordered under double wall. I imagine it had to be in the high tens of thousands range. But nobody was aware of what that local code was. So just an example of codes are important for wherever you're doing business. So, oh yeah, so it just says here, the stainless steel wet parts requires the nitrile gaskets. And obviously it says this may result in a higher, it's definitely going to result in a higher price because you're using stainless steel in your connectors rather than just steel, right? So it's clearly going to be at a higher cost. Just about any type of system that you see that's potable rated versus the non-potable version. The potable version is always going to be a higher cost. All right, so we went through all of that with the single wall. Sometimes you'll see folks specify that they want additional surface area, or they may want additional plate capacity. So let's say you have a building, you know what the load is, you know how the system is now, but you know that down the road there's going to be an addition, and that addition would then have the same performance. It would have the same performance. Oh, you guys can see it. It would have the same performance, but you know that you're going to add another building. You can make sure that we could say, for instance, under the performance requirements, we would say, so you could start off with your excess surface area, or you could even put it under verify. Then next, you could have it under your extra plate capacity. So you say, I want to be able to add 20% more plates later, 30 more, just so that when you do run the selection, so it's because you'll notice that it narrowed down. When you do get your selection, you don't then have to say, okay, what does this have for, oh, this only has 2% extra surface area. What do we have for plates? What's the potential plates? Just makes it easier. On this, once you get to this point, usually it's just, what it does is it sorts it in terms of price. Everything's going to meet your minimum requirements in terms of pressure drop and so on, or your maximums in that case. Provides your lead time, connection sizes. But if you were to let's say you select your first one, you could say, okay, well, in this case, dimension B is 72 inches. So it's 72 inches tall. The frame is 23 inches. That's this here. And D is about 20 inches wide. So that works out well. Versus if you said, let's say as an extreme, if you were to select something like this, you'd say, well, the frame is 23 inches, but it's 88 inches tall, and depending on your room. So just so you can kind of go through here, you can sift through, and then on the dimensions. But everybody's software is going to be, I think, relatively the same, where you're going to want to see, the lead time, the weight, the dimensions, the pressure drop, the performance. Everything else is pretty intuitive. So the next one, you'd be able to click, you'd say, do I want to have a stainless lined ports, or do I want to have flanged ports? If we didn't have NSF, if we didn't have it selected, there'd be a bunch more options. It's where you'd add your insulation blanket and so on. But ultimately, just want to show that you can get your 3D file. You hit save. From there, you'll get your item that you can import into Revit. And then this is really the sheet that everybody's looking for. That's your performance sheet, list of certification, has some dimensions, plate count. Now, if somebody has an existing heat exchanger and you want to find this sheet for their heat exchanger, all we need is their serial number, and we can go back and log it, and then you can get this. You'll know everything from the flow rate to all of the details about, okay, this is the plate thickness, this is the plate pattern. So if you wanted to say, what can I do with this unit? You can go into that rating portion, and you can put these details in and change your conditions and see what's achievable. So I don't think, I don't know if anyone has any questions. I imagine we probably won't have questions until you try it out. But just want to get everybody familiar. How do I get this guy out of the way? There we go.
This is a question
Yeah.
opportunity.
Yeah,
Back
yeah.
to when we discussed the differences between parallel flow and comfort flow, the advantages and disadvantages, something along the lines of there's a lower mean log temperature difference for the parallel flow, but there's a higher Q for the contra flow. What was the benefit of each?
So I'm not aware of any benefit of the counter co. I'm sorry, of the same direction, that parallel flow.
Oh, okay.
We want to have that counterflow. That's going to give us that greatest LMTD, which is going to maximize our given surface area or use of that surface area. You know, if we wanted to achieve the same heat transfer and you had one parallel, one countercurrent, you would require much more, with everything else held constant, it would require more surface area for that parallel current.
Parallel. That's what
Yeah.
coming into this, something, I was like, wait, what's going on?
Yeah, I'm not aware of a benefit. I'm sure that there's probably something in some industry where there may be of like some gradual temperature change, but in that case where you take the hottest and coldest and they're ending at the same point, giving that greatest LMTD, holding the surface area constant would give you that heat transfer rate. I think it was like 25% greater, or a reduction if you were to do the parallel flow. All right, so another quick one. So with these platforms, sure, what does everybody use? Everybody use the Grundfos, Takeo, B&G. Anyone have any experience or preferences?
I like the beam.
Oh, yeah. Thanks, Brad. Thanks, man. Ultimately, a lot of them, it's just like a lot of other technologies out there. They may start far apart and then, you know, eventually we're probably all going to have a lot of the similar features, but this is ours. This is ESP system-wise. On here, we've got everything from the pumps. You make a pump selection. It'll set you up with suction diffusers, triple duty valves. You make either of those selections. It'll give you an air separator. So for instance, if I were to go, let's go 500 gallons a minute, 60 feet ahead, and I were to do let's say a 1510X, you have your conditions, you have any motor details. So if you wanted to say, the default is non-overloading, but if you wanted to change it for duty point, you have some constraints maybe on your motor horsepower. You want to match the existing horsepower, but at the same time, maybe you want to stretch the conditions. You can adjust any of those in there. But I just put the conditions in, selected the E1510X. That's the end suction base mounted unit with the onboard drive. So in this case, I just want to zoom into, how do I do this here? Be F11. Any better? I don't know if it makes a difference. Okay, so just wanted to show you is up here in the header. When if you decide to log in or if you use this platform, one of the things that's nice is that you're able to sort these selections based upon what you're targeting. You know, like I was mentioning before, is that everybody's customers often have different motivating factors. What's driving them? You know, are they saying okay, I've got these space constraints? Or are they trying to, look for longevity, the highest efficiency for now, high efficiency, low upfront cost, but maybe it doesn't have the longevity? You could essentially pick these by saying everything from, you could say, okay, pump speed. I want to have a lower RPM that aligns typically, at least according to the DOE, is the higher the RPM, usually have a lower lifespan. You could say I want a base mounted unit, but I want to have a small footprint. Base mounted units versus inline units typically last longer. All these different things to filter out, or you'd say these are the ones I choose. So I usually look at percentage end of curve. Obviously, you want to know your pump speed because you want to say if that motor is rated for 1800 RPM, I don't want to have a selection even if it looks like it's at a nice point. If my design condition that's rarely achieved is at 1500 RPM. So I like to obviously know the RPM, motor horsepower, duty point efficiency is important, but I think George may have spoken a little bit about that part load efficiency value. So, you have your duty point efficiency, and then it's rarely ever required off the top. Often you're ramping down, and by ramping down your RPM, your position or your duty point shifts on the curve a bit. And so more true in terms of your operational efficiency would be really an average of where you're operating at that part load. And that's PLEV. So I use that quite a bit, especially for any of these selections. So at the top, I did variable speed. You do censored or sensorless, or either both. put the conditions in, select the E1510X. In this case, I can see this model's a 200, okay, so it's a E1510X 3BD. That's the voltage. It's offered in the 380 to 480 and the 200 to 240. So let's say if I were to look at this one, provides your wire to water efficiency. The reason for that is because the motors aren't rated separately. They're just the whole package. So hydraulic efficiency and motor efficiency are all factored into that. Here's that RPM. We have our NPSHR, our horsepower, and our relative price. So what you can often do is you can say, okay, I want to sort by relative price. What are a couple of these where it's 74%? That looks pretty good too. Unfortunately, the PLEV is based off of the hydraulic efficiency. So just the pump, not factoring the motor, at least in the softwares. And so, you know, in the future, I'm sure that what they'll do is they'll put a placeholder or like an assumption of some of these of the motor efficiencies. And in doing so, they'll then be able to use units that have integral drives. Right now, integral drives wouldn't be able to be on the same. So if I were to do something that doesn't have an integral drive, right, like an E1510 without the onboard drive, and I were to run that very same conditions, you'll notice is that PLEV that I was mentioning before will be there. Because what it is it's really just factoring the water side, the hydraulic. So in this case, it says 82.2, so make sure that was filtered to the top. If you wanted to say that, if you wanted to do footprint or let's say floor space, you could filter by that. In this case, the lowest is 5.23, and that's really actually the unit with the highest, greatest efficiency. And we look at where we're at on the curve. You can select the curve. You see your best efficiency points at 85. You're right there. That looks like a great selection. So let's say if you wanted to see more on that selection, right? So all you have to do is highlight it, just click anywhere on it. That'll bring you to a page with all the details. You can look at different curves. At this point, what I would probably do, sorry guys here, let's see if I can, there we go. So usually what I would do is you could add it to, go back, there we go. All right. So on the right-hand side, you can go to add a schedule. You can say it's P1. Then you can say, if you wanted to have a drive on the wall, you can do that. You can put in your voltage. You can put in your voltage, have it find you a model. You select that model. You then say, okay, what's nice about it is that it kind of walks you through. If I needed a triple duty valve, you'd be able to say, okay, well, my suction side, my discharge side is 3-inch. And my suction side is 4-inch. So I mean that's obviously great when you're looking at selecting your suction diffuser. On these, you don't want to have them throttled too far back for the design conditions. I would probably go closer to like this 5-inch where it's 100% open. You don't want to start at your design conditions and really have that be at a 70% close. So you probably select this, and then from there, sorry, I'm moving this guy again. Suction diffuser, you say, okay, I got a 4-inch suction. What would make it easiest? We've got a system side, pump side, everything matches up to that suction size. So it makes it nice and easy for you. But then what you could do is you'd say, okay, at that flow rate, I'm going to have, let's say a 6-inch pipe. So you'd say, all right, well, then rather than having a deducer, I could select that, or I could select the other one. So select, and you add. Now that'll put everything into a package for you. And I don't want to spend too much time on this, but ultimately, where it has over its schedule, you can download, you can send the data. Moving on to the next thing, if you need an air separator, you can say I want a centrifugal air separator. It already imported the last flow rate because you're doing it for that system. You do a search, see the RL5F, you select, add an air vent. So it kind of walks you through a lot of, and I'm sure a lot of it is just trying to get the sale of everything, right? You know, once you select one item, it does make it easier, but you know, I guess might as well rather than trying to figure, okay, what air separator goes on or automatic air vent goes on that air separator, or what blowdown valve would fit it. Either way, so expansion tanks. I know George went through this. This gives you all the details. This is, you fill this in with your details. If you have any questions, you could always click the I portion if you're not sure how something is, or if you need something to help calculating anything, we usually have an information tab. Heat exchangers, that's where we were at. Beyond that, these other ones are less common, but technically like glycol makeup unit and so on. All right, so that is system ESP system wise, and that is ESP thermal. So with your heat exchangers, the two sizing platforms. From there, what we'll do is we'll look at some of the upcoming technologies, some of the other appliances being used within hydronic systems outside of what George covered. But if food's ready, we could probably take a break, or we could do a short section. Any preference? Let me just crank it out, just knock this out of the way. Okay, let's go on. Yeah. Okay. Try share.
I've been pondering the two air separators over there. Are those different brands of air separator? Or are they just different models? And why is one made out of grass?
Which what was that?
Sitting on the display over there, I call them.
Yeah, I think those are two different brands. So it's what is that, a Webstone one, a Bell and Ground? Yeah, Webstone and a B&G. So
Okay.
Webstones are a line that's primarily like valves, and their whole thing to the market is really reducing leak paths. So rather than somebody putting, 6 or 7 valves and fittings together with all these different leak paths and sweating everything or threading everything together, they usually have a solution where it's already packaged.
Yeah,
So-
like that, like big outlet on the wall.
So that one's for a temperature sensor.
Okay.
So yeah, so like if you were to have a, let's say a primary second, so that's a primary secondary header.
I know
And
what the temperature is.
yeah, I mean, I would actually prefer that sensor not be on that and be downstream on your system so that you have a true indicator of what your system is achieving downstream rather than that, because where that is, right now for anyone online, we're talking about the location of a sensor on a primary secondary header. But the where that is, let's say for instance, if you didn't have flow in the system and your boiler water were circulating, that's going to be satisfied. It's thinking you're achieving it when in reality you're not circulating out to the system. And it could be skewed by the imbalance in flow rates versus if you have that downstream on the system side, 10 feet or so, then at least it's likely to only be satisfied if you have flow in that circuit. Of course, yeah. All right, so I gotta be doing something wrong. When you press, was it F11 and it is a full screen, how do you get out of that? Let me try F11 again. There we go. All right. Okay, we can exit. There's a lot more to those slides if you want anything with those heat exchangers. I don't think most of it's not necessary right now. But I'm going to go into I'll just jump into this. This is the same presentation. What I'll do is a couple weeks ago, I had to do a piece for FW Web. Actually, you know what? I think I've got another version of it here. Under presentations, to engineering class. We had to do some presentations on electrification items. I mean, so the reason I call it electrification is because, we really are we are trying to take things from gas and switching over to electric items. So, little background on FIA. So FIA started as a pumping company, but when we picked up a gas product line, so Lochinvar boilers, around 2001 or so. And that's when the size of our company just drastically expanded. I mean, probably tenfold or more. We are heavy on combustion and the gas side. That's really core to our business. And in recent years, we have been seeing the shift. But what always gets me is when, when we have these conversations about decarbonization and really people are pushing for electrification when, they are really two different things. And sometimes they can be both, but it's not always. And let me make sure that this presentation here is full screen. See how quickly we can get through this one.
Some other routes to decarbonization. I'm thinking like, I know if hydrogen can be electrolyzed elsewhere and.
Yeah, I mean, so the question was about how else we can decarbonize and about the potential for hydrogen. Is that right? So, I mean, so hydrogen is great in the idea of like, if you have these, so some of the greatest inefficiencies in the grid are the peaks and the valleys, right? So we have to constantly overproduce, or if there's ever a point where we underproduce, then there's like a brownout, right? So if we always have to produce, that's obviously wasteful. But you have these peaks and valleys, and if we were able to, whether it be a battery or whether it be to store when we have these excess in hydrogen, yeah, that would be great. But there's a lot of challenges with it. With decarb as of right now, so a little bit on this is you're trying to take a perspective of this of like, I have no bias of what technology I want to decarb. I don't think there's anybody with any political affiliation that doesn't say that they want to do right on the planet. It's just usually people debate like to what extent, right? So last year I was the president of ASHRAE Boston. The 2 years before that, the past 2 years, and then for one more year. So I'm the Region 1 RVC for ASHRAE. So if anyone that's an ASHRAE member, I would be the regional that covers New York, New Jersey, and New England for all 15 chapters. And so we meet with state and local officials to have these conversations. And I think that I come from a unique perspective with this company is where we offer gas, we offer electric. I'll give you all the options, the pros and cons of both. But I think that's important because I think that a lot of times when we have these conversations, and a lot of the times when folks are having these conversations with folks and trying to influence them as to why their perspective is better, there's usually something that they're planning to win out of it, right? Whichever side they're supporting. This presentation, along with what I do with the ASHRAE stuff, there's several tools we can use to decarb, but the same tool isn't always the right one. So, for instance, actually, I'll get to that. Actually, I got some charts in here. This is just showing is that that in the past when we thought of heat transfer, a lot of times we'd think of something that was gas generated, whether it was through steam or oil or was burning some sort of fossil fuel, and that's how we were creating our heat for all of these hydronic systems. But there's, as you can see this map, there's a bunch of these states that have tried many attempts to really ban gas. Really, that's not going to be successful. What is successful is that if you spin it from banning gas to instead spinning it to air quality restrictions, then it'll pass, as you saw in like California, and I'm sure every state. So people aren't really doing the gas ban attempts so much anymore because it tends to lose in court, but you can restrict the amount of emissions people put out, which is essentially what you're looking for anyways. But I only mention this because it's important that we're familiar. This is the time that we're seeing the most change in comparison to previous decades. And so, and a lot of folks that are in the middle or later in their career, can you imagine doing something for many decades and then say, okay, now I'm going to take on all of these very complicated technical products with a lot of this nuance to it. And it's a great opportunity for folks that are, in starting their industry experience, because it's not just green possibly for us here in the room, for most of the people that were seasoned before at everything else. So it's a good opportunity for young people, I think is my point. In Massachusetts, there's also significant incentives. These incentives, if you look at the 3-year plan, the utilities, they make this 3-year plan of how they intend to distribute funding and support efficiency every 3 years. and I think it was about 4.5 billion is the size of the pot for the next 3 years. Now, if you look at previous years and previous 3-year plans, we're seeing for some categories, the funding is greater for a lot of these different categories than like the past 15 years combined. So this 4.5 billion is nothing like in the past. This is significant. I mean, I would venture to say is that previous plans were probably in the billion to two at most range. Most years probably even less. So there's significant funding, and anyone that's been tracking in the past, that the utilities really have to distribute these dollars. And it's been a challenge in the past for them to distribute these dollars because it's a lot and they don't have a ton of manpower. And so they have a lot of funding that's more than they ever had in the past. And they already had a challenge distributing that funding back when it was significantly less. So what I'm saying is that projects will be incentivized very heavily. So if you do look at some of these projects now, one of the downsides, so like our gas boilers, significant part of our business, gas boilers, no more incentives en masse. So 2024 was the last of it. But and I think that it's important that we have these conversations with our customers because when we start talking about how do we actually decarb and when is it actually decarbing, because electrifying isn't always decarbing. And so to give you an example, in a couple slides, I've got ISO New England and it shows the grid composition. And now in the winter, when you have these peaks, you could have 30% be oil. You have 50% of it is generally natural gas. Your renewable is usually about 20% or less. And most of it is actually through, burning trash and reheating it. I mean, usually solar and everything is significantly less. So you say, okay, so if that's the grid composition and 50% of it is natural gas, and by the time we have generation, usually you have you can have a 40% loss in generation. So you're at 60% of the actual energy that you put in that you're actually getting out. Then you have your distribution losses. The utilities publicly put out their efficiencies to the outlet just generally in the 30+ range, and on really hot days can be far less. So if you're putting gas and other fuels into a system and you're about 1/3 of it is what you're getting out, you have to have a COP of almost about 3 or 3.3 to really get to that 100% efficiency. Now, if you have a gas water heater, you might be at 96% because you're always running at the lowest water temperature because it's not a boiler. So let's call it even 92%. You're at 92% of gas in to energy versus gas in, lost through the stack, distribution losses. And if you use an electric water heater, then you're at 130 efficiency. So if you're trying to create the same heat generation, you might actually increase your carbon footprint by 2 or 3 times. If it's not a heat pump type. If it's a heat pump type, yes, maybe it can make it so that your carbon footprint is only half of that, or maybe only twice of what maybe a high efficiency gas unit is. But then there's a lot of smoke and mirrors, is what I'm trying to say. So we have to think about not just what we're using for a product, but where's that power coming from? So in Vermont, for instance, very clean grid. I mean, you could practically just have a resistive tank type unit, plug it in, and you're probably you're going to be greener than using just about any high efficiency gas product. I'd say that to no other state. Every other state that I'm aware of has a fuel mix that is surprising when we have these conversations. So, if we're going to say, I'm going to put I'm going to electrify, and you don't have your own, solar, you don't have your own PV on your roof, and you're pulling from the grid, and you switch everything to electricity, not heat pump style, so it doesn't have that COP, but you're just doing like a straight, in out resistive. There's I can't picture any scenario in which you wouldn't actually be increasing your carbon footprint. So you gotta keep some of these things in mind. Now, over time, that grid's going to get better. It's going to be more efficient in its generation, its distribution, and its fuel mix. And then that's usually the argument for a lot of folks is they say that what we're doing is we're putting equipment in now so that later on when the grid is clean, that we'll already have the equipment there. Which I mean is an argument, but then you have to also consider is what is the anticipated lifespan of that equipment. And what is the impact in that meantime? Is it going to be 15 years until? So there's a lot of variables. Now, with having that kind of conversation and being as complicated as it is, I think that rather than simplifying things into people saying, I want to electrification or I want to decarbonize, I think it's important that usually I like to have a conversation with people about what their primary goal truly is. So is it to decarb? All right, great. Let's find the best way to reduce our carbon footprint here. Now, in Massachusetts, pretty interestingly, so in Boston, you have BERDO. Has everybody heard of at least? Okay. Yeah, so BERDO is a Building Energy Reduction Disclosure Ordinance, where essentially all these buildings had to put out all of their utility usage. And they've been doing that for maybe about 10 years now. And I think at first it was to create a baseline so that they could determine, all right, which sectors, whether it was lab space, healthcare, municipal, the power consumption that the average had, so that they can then set like improvements. So they'd say, okay, if you're X per square foot for carbon intensity, the others on average, the best 80% could get to this and set that as a bar. And so, in the past, people would say, I'm going to replace equipment because they knew that they were getting significant incentives. Now, yes, there are significant incentives, but equal to the significant incentives are a lot of, at least the conversations I have with a lot of building owners, that really gets them to switch to, a lot of the electric items that we offer, is because of actually the fear of BERDO. So BERDO has, it's upwards of $1,000 a day is technically what's written in for non-compliance of some of these larger buildings. Now, I would say is that until that actually happens and someone actually pays it, we'll see. But that it is pretty aggressive. So either way, there are penalties for not doing it, and then there are significant current incentives for doing these upgrades. So, it's nice that it's kind of pushing in one direction, but in the past we didn't see any penalties. We just saw incentives for going from a standard to a high efficiency boiler. We didn't see any penalty for not. Other things is you may see a lot of these like publicly traded companies. So they might have their ESG goals, whether it's brand reputation, operating expenses, ROI, all of these different factors may be reasons for people to or not to electrify or to decarb. And I'm only spending so much time on this because I think that so the rest of this, we're going to be talking about heating water using these products. But, we've got some projects out there where the utility will pay for almost the entire project. But at the same time, that utility, that building is likely going to, if you add up their electrical and their gas, even though maintaining some of the gas equipment in there, you'll probably see, a 30% increase in operating cost. And that's just because the cost for electricity in Massachusetts is quite high. So if you make that shift, the utility is going to offer significant funding to do it, but just keep in mind that electricity is at a premium, and that money is going to actually, may not make it back to them in our lifetime for how much these projects are funded, but the operating costs are higher. So if someone's looking at ROI, unless your ROI is also considering, things that are outside of, the purchase price and the operating costs, then it's going to be non-existent. And this is just that piece about the grid mix, and the difference between electrification and decarb. But this is ISO New England. You can go online right now. You can see with the exact composition of the fuels that are supplying our grid. And I think one of them was for another territory. I did one for New England. That's ISO New England. The other one was for like the Carolinas and stuff. I think that might have been the one on the left that has the coal. That's further down the East Coast. This presentation was to a bigger territory. But just to see, and it's good to be knowledgeable about it. And when we start thinking about like renewables, sometimes you'll notice that these different power associations, sometimes they'll consider hydro, sometimes they won't. So in New England, if you included hydropower, you'd be at 17. But people have removed hydropower from calling it renewable here because I think there's some because obviously there are impacts in the environment. And so they wanted to make it, I think, clear that it's not a long-term sustainable all be solution. While you'll see in other territories, hydro is going to be included as part of the renewable. But it's always funny to think of, whether it's the refuse, so it's the waste reuse or waste to heat. And we start looking at it, and wouldn't think of that as being, a fifth of your renewables. But this was taken at, like, I think it was 7 in the morning, it said. So, solar PV hasn't really picked up and stuff. It was no. So silly enough, I didn't think years ago that we'd be offering such a product, but electric boilers, resistive boilers, there's a place for them. And that's something that we offer. This is one that newly came out. We've got larger ones that go up to like 11 million BTUs an hour, but this is the smaller one, just uses our traditional interface. But like, let's say if there are any projects where you have heat pumps, the cost of a heat pump system, like let's call it an air to water traditionally, compared to like a boiler system, is probably going to be in the range of about 7 times the price. And so compared to a high efficiency boiler system, so if I take my high efficiency boiler system compared to my air to water equipment, so I'm seeing about a 7 or even greater difference. So we have to be a bit creative in backup scenarios. So like, with a lot of this equipment that's at that lower cost, maybe, if we had a million BTU load on a building, maybe we do 3 500s so that your spare is only at 500,000 BTUs, or maybe you have a 2N design, you got 2 1 millions. Now with heat pump systems, these air to water ones, you don't want to do 100% redundancy like that with heat pumps, because you're paying 7 to 10 times the cost for something that hopefully you never have to operate on it, like a backup unit. So a big reason is too, is like for the first few years, we're quoting these projects out all these different ways. Before a lot of these projects move forward, when they're back in the study phase, all of these firms were asking the same question. How is it, how can we design a system that's going to give the customers the efficiency, the low upfront cost, and it's about not having your backup be as costly as your primary. And so whether if you're saying the site has to be all electric, okay, well then we'll have an electric boiler as a backup. If they say we want carbon reduction, but there's no requirement to be all electric, then usually someone would say, okay, I'm gonna get a boiler, not even a condensing boiler, because hopefully it never runs. And if it does run, let's say beyond the conditions that are able to be supported by heat pump, it's usually at like, -4 or greater. And at those points, you're not condensing anyway. So why pay the extra money? So you'll see maybe some non-condensing boilers, maybe you see electric boilers, either way as a backup, just because, whenever we and others price systems, and if we price them like we did with boilers before with having 100% backup, the cost is just unnecessary. Like if you or I were designing it for our own building, it wouldn't make any sense to do that. So that's kind of what's piqued the interest of a lot of folks on electric boilers. So this year, this is an air to water piece of equipment. What we're seeing it take off a bit more is on the plumbing side. Who in here does plumbing? You guys also do plumbing? All right, cool. So this is where we're seeing some of the biggest changes too. So this is a potable rated unit. It's called our Veritas. You take that I'm sure we'll make a non-potable version of it at some point, but right now Lochinvar is the potable. This lists out the COP, 513A refrigerant, modular concept, so you just pair them all together. I'm just it'll be a 2-minute skim on products available, and then we're gonna get into some of the piping of these different products. On the left-hand side, those are our air to water units. So on the far left, that's got an integral tank. So it's got that 119 gallon tank and 120 gallon tank with a small heat pump on top with a backup. Yeah.
Is it a water source heat pump or a geothermal heat pump if it doesn't use volcanic heat from the core of the earth?
What is it?
If
It's not.
the selections on the right hand side of the screen right now.
Oh, you just call it a water source. Well, I mean, you might be using waste heat. You might be using some waste heat or some byproduct heat. And so in that case, I mean, it would just be water to water, not geothermal. But I mean, that's why, yeah.
Right, that's something like the ground storage slash like, or ground loop heat pump is different than a geothermal heat pump, and that's kind of like a thing at the office, like people use those interchangeably, but I don't think they're interchangeable. I just wanted to like ask here
Um, now I know that if you go to like, if you really want to see how everything's classified and subclassified, you go to the Mass Save QPL qualified products list. In there, there'll be an option to be able to select an Excel file. If you search if you do that, there's an Excel file. It'll provide commercial, residential products, all tabbed out, air to water, every product. And then from there, you could even do drop downs of, whether you want to have like in Europe, a brine, you want to have something that's rated for a brine solution, or you have there's a dozen different water to water classifications. And when you do that, it'll actually provide, I think it provides it does. It provides their HRI, because they actually, Mass Qualifying Products List actually uses the HRI certifications for their Excel file. And you can even filter in by efficiency, but I think you might find interest in how many, there's so many classifications for the testing, but it's important because they all have different tests. And like a lot of these products, like heat pumps, the testing is so far behind. Like if you look at our, like right here, our Galletti product, and we'll talk about it in a minute. So that's like our 400,000 to, you have almost 800,000 BTU single module unit, hot water, chilled water. Now it does hot water and chilled water. So what we can do is we can get that AHRI tested, and it's certified for HRI 550, 590, which is not made for the heating aspect. So a lot of times, and up until recently, a lot of times everybody in the industry would, unfortunately, well, they would deceive people. Everybody would say, tested in accordance, tested to, or tested in accordance, but not certified, because there currently isn't a certification. HRI is actually in the process of adjusting 550, 590 to cover the heating aspect, but there isn't a standard to even test to it. So if somebody made some outrageous claim, technically there'd be no slap on the wrist, because there is no certification that they could lose their listing to. Now you can get it certified for the chilled water aspect, but the heating. So, but that's only here in the States. Internationally, they have what's called a Eurovent. This is Eurovent certified. So, at least for us, we know that, hey, if someone has concerns about the heating, what keeps people honest, we could say, it's certified for Europe. But I mean, technically in the United States, they haven't been caught up. I mean, even with heat pump water heating, I mean, there's a gap where if like the far one, a CHPA 120, where it's got a 12 kW element, it's got a 12 kW element, about the equivalent for a heat pump in terms of output, so it's probably about 3.5 kW, it's about 15 kW. But ultimately, it falls through the crack of the certifications where the DOE says it's tested to this up until this point, and then once you exceed, I think it was actually like it was a breaker size that it exceeded after that voltage. I think it provides some amperage. If you exceed that, then it's tested to neither. I actually came up last week where there's standard 1300. There's DOE has their stuff for residential. It's kind of funny, and that's why I think it's really important that whenever we look at spec sheets for ours and anyone else's, make sure that when we're comparing products, that on the back of the brochures or wherever it shows a performance, they'll always tell you the standard in which they tested it to, and if there isn't a standard that they tested to, what they will do is they will provide you with the conditions. So domestic, it's easy because they'd say entering water temperature, leaving water temperature, and ambient. Simple. But yeah, that's we were going through some of these challenges. I work with Lochinvar, their product management, at the factory, like remotely on some of these products a couple of years before they come to market. And these are some of the conversations we have to find out. Like if we're developing a product, if there's even a standard to test it to, And if not, we have to, like, I worked with AHRI on trying to get a standard for this, because, if we don't, then anyone can really just make a claim. And it's better for everybody. All right, so that's water to water on the right. This is where anyone that's into the plumbing, where it starts to get a bit fun. So, actually, let me see. I'm actually gonna go to the next one. So, okay, this is actually probably closer. All right, so in this case, we've got 3 storage tanks in parallel, and we've got a brace plate heat exchanger isolating the heat pumps, or the heat pump, which is outdoors, that's glycoled. So that you could glycol well, you wouldn't glycol. So if you glycol the outdoor unit. Some people don't glycol the outdoor unit. They just put like a heat wrap. Every system that I design, or that we design as a company or policy, is do a glycol break. Any of these commercial systems, if power goes out, I don't want to be trusting a anti-freeze valve for something that these systems, like I say, in 7 to 10 times the cost. Yeah, I don't want any damage that's because of that. So we glycol it. Now, on the left-hand side of that brace plate heat exchanger, what you have on going towards that heat pump on the bottom left here, going towards the Veritas, you've got a buffer tank. That's not necessary for ours. Some like our Galletti, we'd want to have additional volume. But that was in there from when this is Galletti, but it's a buffer tank. You could have a buffer tank, less likely to see. You have an air separator. And what you have here is you've got a parallel backup unit. So you have a backup unit, whether it's gas or it's electric. So let's say the heat pump weren't able to keep up, that secondary unit would then kick on, satisfy the heat exchanger. Now this manner of parallel tanks, you're seeing a lot of people shift away from, and there's a reason for that. And I don't like shifting away from this, even for these reasons. So it's this is what you see a lot, what you're seeing a lot of, depending on the refrigerant being used. So that anyone's designed the systems in the past, you'd have these tanks in parallel. One tank goes down, you could isolate the tank, you could use the other 3 tanks, replace the tank, back to business, right? You circulate to and from the storage tank. They call that multi-pass. It's probably increasing 10, 15 degrees at a time. And it satisfies that tank, gets up to temperature. Now, what we're seeing with refrigerants is we had this whole cycle where we're trying to find the greatest performance for the lowest ambient refrigerant. And currently at the lowest ambient, you're challenged to find anything other than CO2 for here in the United States. Now, in Europe, you'll see that people are able to use what they call A3 refrigerants, or highly flammable refrigerants, non-toxic. Here, we just shifted recently into the A2Ls, which are the mildly flammable. So we're very, very cautious here. But in Europe, you'll see that there's a lot of products that are based on propane, or R290. That's the refrigerant. You also see 744, which is the CO2 systems, which are gaining some traction here. Now, I don't expect it'll be long until 290 is in place. I think that the R32, 454B, I think they're for the most part. I think there'll be transition refrigerants until, for any of these outdoor units. Considering that if you have a unit that's outdoors and there's no refrigerant lines going in the building, as of right now, they can't be charged with propane. So we could have 10,000, how many grams are in a large grill propane tank? You could have that, throw that in the back of your truck, and you could have that in your grill. But if you have it in an isolated outdoor circuit for a refrigerant loop, I think the limit is like 130 grams possibly. So right now there's an effort by ASHRAE 15, the safe handling of refrigerants, along with the EPA and UL, along with some other agencies, where what they're looking to do is increase the charge limit, not as high as I think is reasonable, but to like 4,900 grams. I like it if they got closer to 10,000, it would really open up a lot of commercial equipment. But even that, 100 grams to 4,900, if we did that with propane, we'd be able to achieve conditions like 180-degree outlet water temperature at -15. I mean, this is something that can only be flirted with right now by CO2 equipment. Our hands are a bit tied in what we can even use, even though it's an isolated circuit, nothing in the building. But unfortunately, is that when the policy and these things are written, they're developing them for, there isn't enough of a designation for an outdoor monoblock versus something that's connected. So that's a bit of the point. All right, so this year is if you have a CO2 system. So one thing about CO2 systems is that CO2 systems, if you look at like what's out there, whether it's the Watts, it's the, so it's the Lynx, it's the Aegis, whatever it may be. There are some companies out there that are making some improvements, but what they're doing, what the challenge is that they need to have a really low entering water temperature. So like if you think about how we did it previously, where we had the parallel tanks with the parallel water heaters and we circulate to and from, but if we're targeting 140, we're probably coming in at 125, 130 before we're finally hitting that 140, 135, 145. And so, the challenge is if you have inlet water temperature limitations, which they call it a high lift requirement, try not to get too much on the refrigerant side, but and you have these entering water temperature limitations where you're not supposed to enter water temperature, I believe, beyond 70 or 75, depending on the manufacturer. Then what they have to do is they pipe the tanks in series. And the reason for that is to dump all of the heat in the one that's labeled as ST3. And then it travels back and they're pulling from ST1. So this is really what they're heating. They're heating these three. And let's say so that's how when they're filling it up. Now, when there's usage, it travels out of ST3 into what they call as ET1, which is they call a swing tank. The reason they call it a swing tank is that swing tank covers the maintenance load, the recirc load of that building. So let's say if that building, if you had a 10-degree delta on that recirc line and you're coming back at 110 degrees and you started blending that in with their cold tank, really quickly, you're going to be above that limitation of that entering water temperature. So what they have to do is they have to bring that recirc line back to the swing tank that has an electric element. So an electric element essentially is going to be what's supporting that recirc line the entire time, except for when there's draws on the system that hot water then goes through from S3 from the tank. I'm sorry, goes from ST3 and goes into ET1. So when it goes from here into here, that's when, it's hot water that came from the heat pump when there's a draw. But anytime that there isn't, a draw that's able to support the recirc line, which anytime other than the peak, then what you usually do is you usually have an element that's almost constantly running just to satisfy that recirc. And that's to maintain stratification, separation of, you want it to be cold and hot. You don't want it to all be blended. Now, that's the current challenge of the way that the industry uses CO2. There are manufacturers out there that are, trying to come up with solutions for lower deltas rather than having to come in at, 60 and go out at 180. There are different control strategies that people are working on. But as of right now, all the equipment out there, you have these entering water temperature limitations that require series piping. Now, series piping has its challenges in, like, for instance, this drawing. If you have one tank that's down, your plant's down. You need to have a bypass at every tank. I just took a standard drawing of what you see out there. So, so what do you do then? Then you say, okay, well, for backup operation, with parallel, what you could do is you could have it parallel, you could have it where wherever your backup can be shared among all of the tanks. Now, what you see instead is you see that what people end up doing is they end up upsizing this swing tank and increasing the elements. So, because like if this has elements, right, and it's of a high volume, how is it that it could be shared with tanks in series? I mean, I guess you could do a second set of connections, supply and return. And, if the heat pump is off, enable a relay to circulate to and from. People aren't doing that. So what they're doing is when you're in a backup operation, you're almost abandoning the volume that you already have in your storage tanks because, and you have to oversize your swing tank so greatly to be able to support your entire system. Now, if you're able to continue to use the volume from all three of these storage tanks that you already have, you could reduce your element size. So when it comes to hot water selection, it's a balance of, you could have a 12 kW, 2,000 gallon tank supporting a large building, 12 kW, so 40,000 BTUs, or you could say no volume, and I'm going to have an instantaneous. I'm going to need an 800,000 BTU unit. So you got to think of those. The less volume, the more recovery rate I need to have to be able to compensate for those variables. So in this case, if you're not able to use that volume, you have to upsize your volume on your swing tank or your elements, which is a significant impact. And when we're talking these systems, the electrical load is already significant. But in time, I think that some of these strategies will change. But that's just the current limitations that such equipment has. But the refrigerant conversation is far from being over. C-Note, I'm sure you experienced everything from the CFCs, the HCFCs to the cycle, and now it's constantly. So it was ozone depletion. That was a concern. That was a legitimate issue. Then global warming potential, and then now we got HFOs and naturals, and we've really removed most of those concerns now. But now the concern is almost all of the HFOs include a refrigerant as part of their blend is 1234YF, which is internationally identified as like a PFAS, PFAS. And so, I mean, that's the next battle is people are going to say, we don't obviously want to have any more of these, the PFAS, the forever chemical in the environment. So I think that we started at naturals, and I think we're going to be full circle at naturals. The only challenge is that, we don't have policies and technology that's quite there. Even, I mean, in Europe where they have these large 290 products, I'd say that, and in Asia, that's where we'll be, and I think we'll be good then. And then I think that CO2, I think that as time goes on and there's better control of the cycle and they can allow for that lower delta. There's also some companies that are doing multiple cycles in series to be able to achieve conditions that otherwise wouldn't be achievable. So this plumbing now is so different than we did a few years ago. But I think that we will be going back to the parallel tanks when we have equipment that can satisfy the needs of the system without having to modify the system, to make it work. Because doing something like this in series, we're taking there's a lot of trade-offs. And so we could make it work. We say, okay, we're going to put a bypass at each one. And then, what we could do is do parallel to the skid. We're going to have an instantaneous heater that's going to be paired with a pump that fills up these tanks in series, just like the skid did. I mean, you have to get very, very elaborate. No, I've never seen a plan on any project in New England do that. So generally, this is what you're saying. In series, put all the weight on the swing tank. This is the Gletti product I mentioned. Goes up to a 54-ton unit, goes down to -4, produces up to 149. Doesn't start derating at temp down to 14. So, and you'll notice that these characteristics are pretty similar. I think multi-stack is probably the closest to us. I think they're the closest to our conditions. But ultimately, I guess the point that I want to make here is that all of them are going to have this drop off in terms of output and efficiency, right? So as the amount of energy in the air decreases, or the concentration of energy in the air decreases as the ambient gets lower, how is it a heat pump with its air blowing over a coil, trying to absorb over the evaporator, trying to absorb that heat? How it's going to decrease, right, as it gets cooler. No matter how efficient the units are, you'll see that if you go to the qualified products list, you'll actually see some manufacturers saying that their equipment doesn't derate down to -5. Well, the reason is because the unit was rated lower than it should have been to begin with. So when it got down to, let's say, 50,000, it could produce 50,000 BTUs at 0, and it produced 50,000 BTUs at 60 at 47 degrees, which is a lot of times the baseline. The reality is that system was probably set up to create 75 at MBH at that same temperature. So you're seeing a lot of people saying that they don't get a D rate, when in reality, as you reduce the concentration of energy in the air and a unit that has the same exposure, it's got its fan speed, that air blowing over its coil, unless you're able to make the refrigerant a bit cooler, it's ultimately you're going to see these drop offs, and the utilities years ago didn't recognize the drop off in COP and drop off in output, and they were requiring folks to disconnect their gas equipment. But now, and actually the past few years, the the C&I group, the commercial and industrial group for the utilities have recognized, and I think correctly recognized, is that though this equipment can operate down to -4, what's your CO? What if I use my piece of equipment and I go down to -4? What's my COP? What's the stress on the current electrical infrastructure versus if I kick on a gas boiler for 30 hours a year? It makes a lot of sense for a lot of reasons. And so surprisingly, even though equipment might be able to operate at such low conditions, the utilities providing funding on like a tiered amount, whether it goes to 35 to 30, whatever you do the switchover temperature at. And if you just go to, I think that full funding is at like 15 degrees. So, we could talk about how low we can go, but it's like at the same time, if you have a hybrid system, which is more likely the case because you probably had a gas to begin with, you're just tapping onto it. You had equipment that maybe that had like another 2 or 3 years left. You're putting a new system paired with it, and you're just going to let it operate very infrequently. Then it really doesn't really matter how low it operates unless you start looking at it as a backup. But any commercial building, typically any boiler plant, they're going to have partial or full redundancy. I just want to grab a bite real quick. All right, let's start. All right. Yeah, the hydrogen stuff's fascinating.
Well, yeah, I was gonna say, like, I don't know other avenues to decarb other than the existence of hydrogen, and that electricity is like, seems to be the only thing, people think of them as synonymous, but like you said, they're not.
Well, I mean, if with hydrogen, I mean, it's nice in that it can store for such a period of time. Like, there's been a challenge in energy industry in general about storing long-term storage, so long-term battery storage.
Yeah, you like with solar and stuff like that. I've heard it called that. I don't know anything else about it.
Say long-term storage, like let's say you generate power, or you're not using long-term storage.
Yeah, you like, there hasn't been one. It was like.
There's a company called battery. Yeah, I think they just significantly made.
Oh my gosh, I feel like I know this one too. Form energy, yeah, FE, that's why it's, iron. They also had something in West Virginia that they started in, not West Virginia. Yeah, West Virginia, I think it was. They built a manufacturing plant there too.
Really?
So
And I remember
they were trying to do like 24-hour plus or like 72-hour plus storage or something like that.
Yeah.
Of electricity with like high efficiency and low cost.
When you think about the iron's the most abundant substance.
Yeah, literally.
Yeah.
And the engine.
Oh, yeah.
Yeah, or maybe this is aluminum, I don't know.
The question is when was the cooling tower?
Oh.
It got back to my mind in liquid coolers. So.
I didn't make this, I didn't make that one. So that heat transfer one, I was like, I usually take more, like less pieces out of it. And I was like, let's skim through it. I'm like, most of it probably just get rid of, because I think that the example might be decent as like, people think about, but like as a 30-second question, people get excited.
And the other thing is,
Refrigerant.
no. The last thing when you asked me, I said, I stopped working with these things just before heat pump this way.
What refrigerant did you use for that, the refrigerant cycle that you had going on?
Whatever they were using.
What was that for? It was where you froze up a heat exchanger.
Oh, when it was the
Yeah.
exchanger, it was,
What did you just like source a compressor?
Yeah, I'm still using the same system. I just
You just made it?
I replaced the heat exchanger.
Yeah.
And I made sure that the expansion valve is working properly. So what I'm thinking, something happened to the expansion valve. That made it freeze inside. The heat exchanger froze it from inside.
What was the, so what are you using it for?
House air conditioning.
Okay.
So I
So
had,
did you, now, was this something that was originally produced and that you?
no, I designed it.
That's hilarious.
And I'm still using it. I have, you can have as many zones as you want. I'm using just, fan cords all over the house. And running
What do
chilled
you
water
have?
system.
What do you have for a condenser outside?
One of the carriers, 4 ton.
This seems like some, like an enable disable.
There's one thermostat in the house controller. And then I put some limiters so that the water drops. With a certain temperature it shut there too, so it doesn't freeze again.
Yeah, it's a site.
I built my own program.
You just use the basic.
Relays, I just put a system of relays. As a programmer.
I know you. The interface or just.
No, just.
Unbelievable, like what you do with like a handful of relays. Like, the Koja stuff, it was funny, because people were really expensive panels. $400 in relays, you know?
There are relays. That's it, but it's like.
Yeah.
But now I'm thinking this to change in the church music.
Control everything.
Right, yeah. But I should go to that one thing. Because the people have worked hard on making it like it's small but it's pretty simple. All the characters here, and there's the only thing we did was to do it. Like our ground source heat pump. There are probably several different extensions that are real worth talking about. Whether it's one that defines that this is a grid ground versus find a well and see the well or something like that. Like yeah, I mean, that's where you go. That's where. Yeah. You're trying to. Yeah, yeah, but exactly. A lot of people in Houston are like converting their oil drilling into ground source. I think that's the best. That's right. You know, the people who are like the right source. Let's do that. Build it. And you have to very. How would you go? Change the gas. Change the gas. No. Yeah. Yes. Yeah, well, I probably. Ground here. Yeah, like that's out there. Yeah. Yeah. We have no sandwich. Let's make it as if it's very nice. Because rather than getting it slated here, yeah. Yeah. Order. Yeah, right. Just like
How do you do it like that? Just produce it, the air stays in freeze, nothing, the volume is not that much. Just even if it goes to the laminate floor, it will freeze it.
Reminds me of like if you have the same small fan and you put it like on a baseboard system to increase the exposure of the water. And then
I want you to rest here, you talking for. Yeah. That can have. The bakery, like. Yeah, like. Just, yep, this is the, like. Yeah. Just put over here, over here. Okay, 1 5. Little thing. I will show you.
Yeah, I wonder. You know, you would just, so we're all with the plates meet.
In this section.
So I can see, yeah, so like we had, because like for instance, if there's a raised plate. If there's a raised plate, all the sides would just sit in, and the edge, if two ends, and then the gasket would. Yeah. It's almost something like, I feel like, well, the only thing is that they're pressed so hard together. And I think it might only be the bottom.
Even if it is not raised, even the regular big one. And you actually, the small one, you don't care about it, it's bigger ones.
I wonder though, is. If you had the heat exchanger sitting in. And you say you have a plate, and then another plate. I believe that the outer ridge may be sealed like this, and it's just the bottom that's open. So it would have to be open and not sealed at 2.4.
This.
Oh,
This as
you're talking about similar to like water conditions, yeah.
That one would increase the efficiency.
You know,
No, I invented what?
we just put two plates and then put an air bin. Then it technically makes the double wall.
Because there is no electricity.
Yeah, so the purpose of one.
Or actually even make it with pins in between us. Between the two plates, big pins, that sort of raised here and raised here. Then the conduction happens, but the gap's still in. That's the third way.
I guess it is that. Like ridges that touch that act as an additional conductors, but at the same time, wherever it touches. Just can't be too large of a space without a gap, or then there is a hole.
Even if there is a gap. One day I was doing a project for somebody. And a furnace and had a huge house, a huge building. And the one who makes the fertilizer, what do you call it? The insulation that they pocket life. What's born? What's the insulation there? Per wire, per light. So he used nothing but per light in that furnace, and the furnace had to rotate all the time. And he posed that per light, the stones from top was light in the bottom. Because the fire, it's true. And he said, like this, the energy wasted. What do I do? What can I help? I need the house with? How can I collect that heat? And, so I came up with an idea. The furnace, that's like a heat. I came and then put 8 heat exchangers around it without touching it, with the air gap. Then it rotates inside it, and the plate is collecting water. In.
Was what part of the furnace was producing the kind of like waste? heat? Was this the, like, the stream of the conductor?
They combust,
Or sorry,
the actual,
conductor?
they actually shoot either gas or one. There it is. And the blue crushed steel.
Okay.
And as it goes inside it, explodes and becomes insulation. So we usually take it and repack it and eat it. But we use wasted it. We didn't know what
Oh, I
to do with it.
agree. All right. That makes sense. This goes on for a long time, some period of time.
24 hours.
Oh, all the time.
Oh,
So it's happening. Okay, so the insulation burns up eventually, and so it needs to be continuously replaced.
no, the insulation is taken out and sold.
Oh,
Okay.
okay. This is a manufacturing.
Then I didn't have the time to sit down and plan to read what I need. Give students in the class. So when we get A, if you do the calculation, we will give them all that. Yes. And I told them where to get it. You don't have to work superfluous. So we did. In a week, and throughout the whole thing, calculated and we did.
The heat pump system that needs.
Just like hands-on,
Yeah.
hands-on stuff.
That's like the question that I gave you last week.
Well, so
Given the
it came back
question.
to that, I don't know how satisfactory it is, but it's a stack effect answer. Yeah.
The number you gave me is good.
Yeah, 19,400.
Yeah. Actually, the one who came up with that idea is my son.
Okay.
Because he came up with a great idea. But I told him, he said, Dad, calculate it for me. I said, let me think about it. So if the number is right, he can make a good amount of money.
It's the actually 1997 from the Russell handbook, that he needs to trust. I think we're gonna grab one more sandwich before we. Okay.
Yeah.
Almost done, almost done.
Okay, all right. Let's see.
This one, it's this number that we.
We know that. This, I'm looking at front today, so it would be easy for me to run down every detail.
Was everybody seeing a lot of studies, or we went through this phase where we were seeing tons of studies. I feel like we were putting so much energy into every project because rather than just doing it one way, we'd look at it like 4 different ways. And I feel like most of the industry is kind of done with needing quotes on every option. 'Cause they're getting They're done a few times, it has an idea what kind of designs are gonna end up with. Here it is. It was deceiving. And it made it seem as though there was a ton of work going on because, you know, I would be working day and night, not keeping up. And in reality, because you do look at the same project 4 ways. So it's 4 times the work with the same, which, you know, with this stuff and the upfront cost, you know, unlike a lot of times, like, so I don't see when a project sells. So I help design, facilitate all of that. But like rarely do I even know down the road or see or work on it later unless, you know, there needs to be some help with it. And so I don't always have the best pulse on, you know, where things are, but I have noticed, at least from conversations, that, you know, of the electrification projects, you know, it's far less than the gas that actually move forward. At least that what I've seen. So it's just anecdotal, but you know, and a lot of times it's that upfront cost or, you know, so on. But yeah, so there's a period of time where we look at every project like 4 different ways, and then it'd be less likely to move forward than, you know, a project that maybe you worked on last year. This right here is just an example of something. I made some adjustments to it. So each let me see here, each project that we work on, you know, we'll put something like, what is it? It's not full screen. You put something like this together. Let me do it. All right, well, that doesn't seem to be working. Oop, wrong button. All right, but either way, what I want to show you here is that this is that similar system. It's just not domestic anymore. Now we're looking at space heating and cooling. So in this case, we had a building where we had a couple of boilers that were existing, and they had a few chillers that were failed, which is typically the common story. Like, you know, if there's an existing chiller, people aren't usually just pulling it out unless it's close to its end of life. But this is an example where the boilers maybe have a couple years left. The chillers are at the end of life, and so we look at the cost of replacing the chiller. We look at the potential fines down the road. I'm sorry, this is I updated this one. This is now Beverly, but this was off of something that we had that was actually in Boston. So the customer at the time, same design, customer had their existing boilers, they had failed chillers, and it was along the lines of um, uh, actually, you know what? I think I'm going to fire. Ultimately, is that the utilities on a $1.1 million install of everything from expansion tank to air separators to heat exchangers to pumps to, I think it was the 3 chillers. Is about 1.1 million installed, and the utilities provided 890,000. And so, and that's because it wasn't low income. Now, certain areas that are, you know, moderate to low income, certain regions, like I think there's a Target Dorchester right now. Basically, anything in Dorchester, I think, is going to be almost 100% funded. And so, the thing is that with these, it's often when we started to look at it in Massachusetts only, because of the incentives and because of the potential fines down the road, is that it actually ends up, the more costly package ends up being the lower upfront cost scenario because of the incentives. Now, also to be clear is that incentives aren't coming from just anywhere, you know, they're coming from everybody that's paying. So, you know, if you receive these incentives, you're paying back into it because you have a pretty high electrical cost. So you're paying back into the pot. Now, the question a lot of people have is whether it's always balanced. Like, for instance, if you do all these electrification upgrades and you get tens of thousands in incentives, but then all of a sudden you get you get enough PV that can support your house, and you really are just paying, you know, 15 a month to maintain your line, but you're not paying that premium on your power anymore because you're producing your own, but you just pulled out of the pot. You know, so there's a lot of these scenarios in Massachusetts where, as time goes on, we'll see who's left holding the bag. The unfortunate thing is that it's probably pointing towards people that are the most vulnerable, right? You know, you're not going to see a lot of the low income households spending 50,000 on PV. And so if they're the ones that everybody's pulling out all their incentive dollars, you know, getting all their incentivized for all their nice equipment, and then So if they have to do panels, then, the people that don't have the ability to switch off are the ones holding it. So there's a challenge, but, this is the same challenge that you see in all parts of the country. I think we're just a little bit further ahead in that conversation, but, ultimately, I think that just like almost everything else in a lot of these in this industry, where we've kind of come full circle in design, whether it's refrigerants, whether it's how to even create a domestic water system. You'll see like that 2000 kW, sorry, 1200 kW, 2000 gallon tank is something you might see in like the 80s. Then by, late 2000s, it was all instantaneous, no storage volume. And we're kind of going full circle where now we're doing the high volume so that we can have a low generation, a small heat pump, so that we can make sense of the price. And if you're going to put your money into something, it'd be nice to put it into something that doesn't have moving parts. So a lot of times we go full circle, and I think that was with commercial buildings, where there's an option. I think that here in Massachusetts and anywhere that doesn't have a perfectly clean grid, or that doesn't, then it is the carbon conscious to have a hybrid scenario. So in this case, this is a hybrid system where they're existing boilers. What we're doing is we're providing a glycol circuit, heat exchangers, that glycol break. We're circulating to and from that heat exchanger. We're pulling off that heat exchanger. If it drops below 15 degrees, at that point, cut off the heat pumps, kick on the boilers. And then once it's above 15, then we kick it back over the heat pumps. So a couple benefits of hybrid systems is also that as your output decreases, as your ambient decreases, we only have to size it to whatever that switchover is going to be. So if you're going to say, hey, my point of diminishing returns for my incentive dollar is around 20 degrees for the most part. You say, hey, at 20 degrees, my heat loss in the building is X. I can buy a heat pump that derates to X, rather than having to buy an even larger heat pump that the derate will cover you down to 10 when maybe you don't get incentive dollars beyond that, and your operating costs are higher to operate. So it really depends on the scenario, how clean the grid is, what your customers' goals are. I think that's the most important thing up front. And like the conversation before about people putting labels on things. I think if people have information as to where things come from and how things work, it's important before purchasing such expensive equipment. So I just want to give that one drawing example. And then something that is no longer, pains me to say, but cogen, it's another thing that I think is going to be cycling in and out. And so there was a period of time where this was kind of like a miracle device for the utilities. I was on the working group representing manufacturers about 4 or 5 years ago, when they were developing not this 3-year plan, but the prior 3-year plan. And we were able to achieve 2 3-year plans ago. All right, so maybe more like 6 years ago. And what we were able to achieve is that for the highest efficiency cogen, we were getting like $2,400 per kW for the unit's production. So at a 24 kW unit, we were getting upwards of like 50,000 incentives that would go to the owners, and the system only cost about 60. So a good portion of it was covered. And the reason for that is this. And so this is coming out of Denmark. We used to sell it under the brand through Lochinvar. Now, since then, they are now their own company here in the US. The Denmark company had come here. EC Power produced it. It's a little micro cogen. They call it micro because it's below the 25 kW. But I think that this is going to be something that we're going to see a lot more, that is something from the past, but it makes a lot of sense for the future. But everything to doing with heat transfer with water. Ultimately, what you're doing is, rather than having your power plant produce your power and it has 60%, and a boiler being at let's say 90% for the 10% loss, versus CHP, you're at 7% loss. If you factor in, if you take gas, it's basically like a liquid cooled, like jacketed generator that's super efficient. So if you take gas, something that's more than 50% of the grid composition, rather than having the generation losses, through the stack and all the thermal losses and distribution losses, what if you had them at the building? So not only are you producing power for the building at 24 kW, but you're also producing about 160 MVH. And so a lot of the buildings that I designed, I think 11 systems, in each one of those systems, on average, including the maintenance, was about $20,000 to $24,000 a year in savings. But I would also argue is that what's more significant is probably the carbon reduction versus if we had gone to some other solutions. So the utilities, they used to have great incentives for such products. But this last 3 year, not this 3 year plan, but the last one, they actually removed it. So cogen, if it's burning gas, nothing, no incentive whatsoever, completely off. And I know that in recent years there's been a trend for decentralized, right? So whether it's blockchain, it's the decentralized ledger, the mindset. Well, same with power, right? So when it comes to grid resiliency, right? So if you want to have security, resiliency, all these sorts of things, we need to diversify. We can't have one plant covering this whole territory. We need to diversify. So point of use is great. So you're able to have your backup power. You're able to, rather than having thermal losses through the stack that everybody sees as they drive by any power plant, all those heat losses are going into your building. And so you just need to find a way to use that heat. So anyone that's trying to, show you a cogen system, the most important thing to look at is maximizing your runtime and making sure that your runtime is not dumping the heat. Some folks would, and we don't sell this anymore, so I'm just telling you just in general, but you'll see a lot more of it during your career is you'll see a lot of dump radiators. Some folks will say, hey, well, I can get this thing to run 18 hours a day. Come to find out it's got a radiator outside that's blowing all the heat to the neighborhood. But it's cheaper to use that power generated from that than it is from the grid. So they'll try to keep it cranking, but then you're going to pay a high maintenance cost. So there's a lot of games with this. What I just want to show is that if you do anything like that, like cogen, you want a base load. You don't size it for the peak. You want it to just be cruising all day. And this is just the example of what we had, but it's a small unit, 24 kW, 160 MVH. It's essentially an industrial Toyota like deep wall 4-cylinder engine. So it'll look like it was about the volume of a oscillating fan. So this is where it gets fun. So what I'm saying is about that runtime. So whether it's heat pumps, where you want to reduce the number of cycles on the compressor, everything comes down to even boilers. You want to reduce those number of cycles. So how do we do that with a water system? And that's when it gets really important to understand the sequence of a system, what enables what, and how things are controlled. In this case, what we did is I said, all right, we've got a building that space heating, the whole fall and winter, unit's going to be cranking away. How do I get it so that this thing is going to be running other than in the heating season? And the best scenario to be able to come up with was for domestic water. And so domestic water, we essentially I made it stage 1. And if it couldn't keep up, then I'd enable on the bottom right those water heaters. The heat pump, the cogen would fill like a reverse indirect. Everybody familiar with reverse indirects? So reverse indirect is, so an indirect, just traditionally, as people describe them, an indirect water heater is a storage vessel, domestic water with a coil. In that coil is non-potable water, which is the water in which you're heating the tank with. Now, reverse indirect is where you have your non-potable heat source water in the volume side, and your potable water is in a single pass in the coil. So it's backwards. That's why they call it the reverse indirect. So that's what that tank is. And so the cogen would fill up that tank, and we'd circulate to and from the storage tank from the reverse indirect. If it can't keep up, kicks on stage 2. That's that water heater. Kicks on that water heater. And, it's funny. Sometimes it's good to try to get into some of the details of a lot of these systems, because you might realize that sometimes the advanced controls aren't so necessary. Like a lot of these systems, if you put a control package on this, it could be upwards of 20,000. We're able to put this and actually more advanced sequence together, and it probably costs about $200 in relays and about $500 in electrician's time. So it's really good. I know we didn't have a section on relays. I know that that's more it's electrical, but when you're sequencing hydronic systems, you can do some really cool stuff pretty simply. Then what I said, the stage 2 was water heater, and then space heating. If if I knew that my boiler contacts, my lead boiler contacts had enable, I know that I had a heat demand. If I had a heat demand, I'd kick your circulator on to dump the heat. So we try to get these things to run like 16 plus hours a day. And Yeah, that's how we achieve about 20,000 in savings per building on an item that, say, 60,000 installed, probably about 100,000 it was the customer, but that got shut down because of the shift away from gas movement. I think that, in the coming years, everybody that really actually cares about the subject and that genuinely is trying to solve a problem, I think that we're going to come back to the solution of a mixed bag, but cogen is going, I think almost 100% is going to be revived, just in that we have trillions of dollars worth of natural gas distribution lines that, why abandon? Our electrical infrastructure can't support even what we have, let alone what's in the future. So what if we had a little generator that's super low NOx, that you're absorbing all the weight that would normally be waste heat off, and you're actually able to utilize the infrastructure that we're abandoning, and then pull off of the grid that's overloaded. So logically, it just makes a lot of sense. And this right here just shows the impact in comparison to if you were to have a boiler and use like grid power. The equivalent of one system like this is the equivalent of pulling 14 passenger vehicles off the road. So one part was today's talk was I just wanted to focus on that there are a lot of products that interact with hydronic systems that we may not see day to day, but there's a place for them, and also maybe think differently, or not think differently, but to question everything in terms of when there's a solution that's proposed that it might not always be the best, and sometimes the more obscure might be the right thing. But I hope I at least piqued that interest. So, any questions? Anything that anyone's worked on or working on that's a bit progressive or different in technology?
There's heating, our strategy was to provide a backup boiler, as one does. Would cogen work for that situation? Like how would this technology fit into that?
You said for backup?
Yeah.
Yeah, you wouldn't want to use cogen as backup.
Yeah.
So cogen and these heat pump systems. So cogen, the reason that you wouldn't want to have it as backup is because the return on investment is highly dependent on the operating hours. And so you would want to have that be the primary. And then when it comes to heat pump, why pay several times the cost for something that, is a backup and hopefully never runs? And that's where, never thought there was going to be a place for like electric boilers, but surprisingly, people are getting them. But that's because, if you're going to cut off gas, you're not going to pay 7 times the price for something that hopefully never runs. But yeah, there's even further technologies out there where, there was even things in development for different manufacturers, from heat pump systems that combi boilers that can be instantaneous. So you hear some people, oh, here's I just try to arm people with some of the silliness is, if someone says that there's a instantaneous heat pump, question it. And the reason I say that is the reason we oversize the storage is so that we can reduce the generation requirements of the heat pump, so we can shrink the heat pump, because that's the costly item. If something has to be instantaneous, then its generation has to be significantly greater, because you don't have any storage, right? So like we were saying before about, you'd have a 12 kW, so 40,000 BTU, 2,000 gallon tank supporting a building, 2,000 gallons, but only 40 kW, or you'd have to require 800,000 BTUs and no storage if it's instantaneous. So everybody's shifting to volume to shrink the heat pump to reduce cost. So instantaneous wouldn't even make sense. But you will hear some people out there saying that they have an instantaneous unit, and the reason is it's kind of funny and deceiving. Is there's a couple companies out there. What they'll do is they use the heat pump to heat up a glycol in storage tanks, and then they have a coil, reverse indirect. Then they put a coil in there, and so the domestic water is instantaneously heated. But whenever someone thinks instantaneous water heat, you think no volume, no standby volume, right? No, they just have 200 gallons of a glycol tank that's not storage volume, that's a thermal battery. Well, it's like, well, technically, if that's potable water, that'd be a thermal battery. So there's just saying that there's question everything, from us and everybody else. I mean, I try to be as transparent because it's complicated enough without the line. But, all right, well, if anyone has any questions down the road, so I'm the contact for FIA, anyone in the engineering segment, I'm the contact. So that's all I do. So we have folks that cover the contractors, commercial, residential, people that cover the wholesalers. My whole job is the engineering community. If you guys need pricing, anything like that, I facilitate that. I'll work with Brad and Craig and everybody, and we'll get you a package. So that's my job, and I like how we segment it because it's nice that someone represents a wholesaler, someone represents an engineer or contractor, that people have someone to fight for. So like if something's wrong on a plan, my job is to fight for you guys when somebody else might be, working with a contractor and they want to fight for the contractor, that everybody's represented. So if you've probably seen it a couple times. Yeah. So if there's any questions, any projects, even if it's not something we offer, they're just curious about like what's a spin on it. I'm happy to share anything that I've come across. So thanks everybody. 2.5 hours.